A plausibility argument for the most beautiful equation in mathematics. We begin with a proof of the distributive law that's based on the idea that we can consider a rectangle as two small rectangles, calculate the area both ways, and we achieve the identity shown in red. We use the distributive law on this expression here, and we see an expression that involves minus 1 squared, and it can be solved to show that minus 1 squared is plus 1. Therefore, I is equal to the square root of minus 1 is imaginary because there is nothing that can square and give you a minus 1. Exponents can be viewed as repetitive multiplications, m times, where m is an integer. And based on that definition, we establish a simple multiplication rule shown in red at the bottom. We can use this rule to raise a number to a power if the power is not an integer. For example, what does 5 to the 1/2 mean? We multiply by itself, we discover that 5 to the 1/2 is just the square root of 5. It can be generalized to irrational numbers. For example, pi is very close to 314 over 100. That's one approximation. Rules for raising imaginary numbers to integer powers are very easy. I cubed is I squared times I, which is minus I. The pattern is very easy to learn, always involving 1 or I plus or minus. Consider you're standing next to a wall, and at every step you cut the distance in half. The calculation shows that this series here is equal to 2, and that's known as a power series. Here's another power series expression, and if we take x equal to minus 1/2 and substitute, we recover the previous result. We have to be careful with power series. They don't always converge. For example, if x equals 1, we get an alternating power series that seems to be unable to make up its mind between whether it is 1 or 0. But if this series does converge, we can prove this identity by establishing that this product equals 1, and we do it using the distributive law. We multiply these together. One term is a power series, the other term is another power series. Note the cancellation, yielding the result 1 that we need. In 1728, Euler was working on explosive forces in cannons when he wrote this equation down. Euler's number is obtained by setting x equal to 1. We can't prove this expression, but we can verify it by graphing polynomial approximations, and if x is less than 2, 4 or 5 terms gives us a reasonably close approximation. If we insert I pi into this expression and write out the first 10 terms using a calculator, we can combine the real and imaginary parts and get an expression that is quite close to the established value, which is e to the I pi equals minus 1. In summary, we took a rectangle and used that to establish the distributive law. Using the distributive law, we could show that minus 1 squared is plus 1, suggesting that the square root of minus 1 must be an imaginary number. We begin our journey into powers with integer powers and establish this rule. This rule allows us to extend powers beyond the integers to the fractions and even irrational numbers. A power series is an infinite sum of numbers that adds up to a finite number, and in this case we can work out that it is a finite number. Power series are very compatible with imaginary numbers because imaginary numbers multiply nicely when you're raising to an integer power. Using the expression by Euler for a power series expansion of e to the x, we can first verify that it's true by graphing it, and then we can substitute it into a calculator when x is I pi, and find a numerical result consistent with the theoretically accepted value of e to the I pi is -1.